Okay, this problem says test the following series for convergence. So the three series are 3 to the power of k over k squared, 5 to the power of k cubed, and e to the power of negative 2k. And all three series are from k equals 1 to infinity. Okay, so anytime we have a where we have series and we want to test for convergence / divergence, the first step that we should always do is just make sure that the series isn't divergence. So to do this, we're going to use the divergence test. And the divergence test is just like a quick, easy test that we can use to rule out kind of obvious cases where a series is divergent. So if the limit of as n approaches infinity of an, where an is the nth term in a series, is not equal to 0, then the series diverges. Okay? And then else, if we get any other result besides, if we get, I'll rewrite it. The series diverges if the limit is not equal to 0. If the limit as n approaches infinity is equal to 0, the result is inconclusive. So that's important. It doesn't mean that the series is convergent. Okay, so I'm not going to go through it right now, but if you do the divergence test, we can easily see that the limit for all of these series is 0, meaning that the result of the divergence test is inconclusive, and we have to use more advanced methods to prove convergence or divergence. Okay, so let's take a look at the first series. The method we're going to want to use for the first series is the ratio test. So I'll first explain the ratio test. So the ratio test says that if the limit as n approaches infinity of the ratio of two consecutive terms in the series is less than 1, the series converges. If it is less than 1, if it is greater than 1, the series diverges. And if it equals 1, the series the result's inconclusive. So inconclusive. Okay, so the reason I say that the ratio test is a good option for the first series is because we have this power, this constant to the power of k in the numerator. So I'm going to apply the ratio test right now. So the limit as k approaches infinity of, now if I take the ratio of the an plus 1 term and the an term, I get 3 to the power of k plus 1 times k squared divided by 3 to the power of k times k plus 1 squared. And so now what happens is I have 3 to the power of k plus 1 in the numerator and 3 to the power of k in the denominator, and that works out really well because it cancels, and all we're left with is 3. So the reason that ratio test is a good option here is because of this constant to the power of k. Okay, and then we're left with k squared over k plus 1 squared. Alright, so now we just have to evaluate this limit, and we have our constant 3 up in front being multiplied, and essentially all we care about now is this k squared over k plus 1 squared. Well, the only thing that really matters when we have the ratio of two polynomials is the polynomial in the numerator with the greatest degree and the polynomial in the denominator with the greatest degree. In that case, we have k squared on the top and also k squared on the bottom, because if we expand this out, we get k squared plus 2k plus 1, in which case we take the ratio of the two greatest degree polynomials. So the limit of k squared over k squared would be 1. So this evaluates to 3. And if you want like a more rigorous way to show that the limit of this fraction here is 1, you could also use L'Hopital's rule. Okay, so that means that since this limit is equal to 3, we'll look down here, greater than 1 means the series diverges. And so we can say that this series diverges by the ratio test. Okay, so I'll cross that out. Okay, the next series is 5 over k cubed. We can show that we can use the p-test on this series. So the p-test states that a series an, which equals 1 over n to the power of p, converges if p is greater than 1, and then diverges if p is less than or equal to 1. Okay, and so in this case, that would mean that 1 over k cubed converges by the p-test. But our series is 5 over k cubed. It should be pretty intuitive to see that, okay, if 1 over k cubed converges, 5 over k cubed also converges. But if we want a more rigorous proof, we can use the limit comparison test. So limit comparison test, which states that for a series an and bn, where the limit of an over bn equals c, where c is greater than 0 and not infinity, either both series converge, so either both an and bn converge, or both diverge. So in this case, if we wanted to show in a very detailed manner that 5 over k cubed converges, we can use a limit comparison test where an is 5 over k cubed, bn is 1 over k cubed. The ratio of those two series is 5, which is greater than 0 and not infinity, so we can use the limit comparison test to show that this series converges. So we can write down that it converges by p-test and limit comparison test. Okay, and the last series is e to the power of negative 2k. Okay, so the trick for this series is to notice that this is a geometric series, because the first term is e to the power of negative 2, e to the power of negative 4, e to the power of negative 6, and so on and so on. So that means that our common ratio, r, equals e to the power of negative 2. And for a geometric series, converges if the absolute value of r is less than 1. In this case, r is 1 over e squared, which is less than 1, so that means that this series converges as well. And I mentioned earlier that you can use ratio test in the case where we have a constant to the power of k or n or whatever our variable is, and that also applies in this case. We have e to the power of negative 2 to the power of k, so we could also use the ratio test, but it's much faster to realize that this is a geometric series and do it that way. So the first series diverges and 2 and 3 both converge, so our answer is C. Okay, problem 2 says the series negative 1 to the power of k over k squared from k equals 1 to infinity is convergent by the alternating series test. According to the alternating series estimation test, what is the smallest number of terms needed to find the sum of the series with error less than 1/5? Okay, so first let's go over the alternating series estimation test. So suppose we have an alternating series A we can say the following. So we can say that Bn is the series such that this is true. Basically, it's like the non-alternating version of the alternating series. Okay, in that case, the alternating series error bound, which we say is Rn, so this is equal to S. S is the sum of all terms in the series. Sn is the sum of the first n terms in the series. So we can say that Rn is less than or equal to the n plus 1th term in the series B. So this equation is essentially the alternating series estimation test. Okay, so we know that we want Rn to be less than 1/5, and we know that Bn plus 1 is equal to 1 over n plus 1 squared. Okay, this is from the problem. So now, since we want Rn to be less than 5, that means that, and we know that the Rn is less than the Bn plus 1, we can say the following. And we want all of this to be less than 1/5. Okay, so essentially the important part now is, now that we have this equation over here, this relation, we can use this to solve for n. So we'll just start, since they ask us to find the smallest number of terms, we can start by plugging in each value starting at 1. So if I plug in 1, I get 1 over 1 plus 1 squared equals 1/4. That is not true, so 1 is not our answer. If I plug in 1 over 1 plus 2 squared, that's equal to 1/9, which is less than 1/5, meaning that 2 is the smallest number of terms needed to find the sum of the series with error less than 1/5. So 2 is our answer. Okay, question 3 asks, which of the following series converge? So the first series is 1 over n times natural log of n squared, the second is 1 over n times natural log of n, and the third is negative 1 to the power of n over n times the natural log of n. And all three series are from n equals 2 to infinity. So anytime we have a question asking us about convergence or divergence, we want to start off by using the divergence test. So the divergence test states that if the limit of an as n approaches infinity is not equal to 0, the series diverges. If the limit as n approaches infinity of an is equal to 0, that means that the results of our test are inconclusive. So we have to use a different test, basically. So if we apply the divergence test to each of these series, the resulting limit is equal to 0, meaning that the result is inconclusive, so we have to use a different method to prove convergence or divergence. Okay, so we have the ratio test. For the first two series, we can use the ratio test, the comparison test, the limit comparison test, or the integral test. So let's start off by considering the ratio test. The ratio test isn't a good option here because we don't have a factorial or a constant to the power of n. The ratio test tends to be good for situations where we have something like that because it makes it really easy to cancel things out. We don't have anything like that, so let's not consider the ratio test. Okay, next for the comparison test. Comparison test is really good when we have a series that is very similar to something like either a geometric series or a series that we know converges, like a series that converges via the p-test. In this case, we don't really have anything like that either, because 1 over n does not converge according to the p-test. The limit comparison test would be good also if we had something that was similar to a series that we know converges. So same situation as the comparison test. maybe not a great choice here. So all we're left with is the integral test, which we saved that one for last because it's not fun taking integrals. Okay, so the integral test means that we essentially take this series, and we consider the equivalent function. So we'd had 1 over x times the natural log of x squared. And if the value of this integral is finite, then that means that the series converges. If it's infinite, then the series diverges. Okay, so now we have to find the antiderivative of this integral. So the way I'm going to do this is by using u sub. You'll notice that we have natural log of n here, and we also have 1 over n. And 1 over n is the derivative of natural log of n, which is why u sub is a great choice. We can set u equal to natural log of n, and du equal to 1 over x. Okay, I misspoke. It should be natural log of x. Okay, so then our resulting integral is from 1 over u squared du. And now that we're doing u sub, we also changed the lower and upper bounds. So the lower bound is going to be natural log of 2, and the upper bound is going to be the natural log of infinity, which the natural log of infinity is essentially infinity as well. So, and technically we're not, actually we can write natural log of infinity, and then now we can rewrite our integral properly, because we're not allowed to integrate to infinity. We have to say the limit as b approaches infinity of natural log of 2 to b of 1 over u squared. So the antiderivative of this is equal to negative 1 over u from natural log of 2 to b okay, and this is essentially, if we plug in b and natural log of 2, this limit is essentially equal to the 1 over the natural log of 2, which is finite, therefore series 1 converges. Okay, so the second series, we can do the same thing. You'll notice we have the same situation. We have 1 over n, and we have natural log of n, so we can use u sub again, where we set u equal to natural log of x, and du equal to 1 over x. It's from 2 to infinity, so this is equal to the integral from natural log of 2 to infinity. I'll go ahead and I'll add our limit right now. So after I plug it in, I should get 1 over u du. Okay, and so now the antiderivative of this is natural log u from natural log 2 to natural log, so to b. And if I write this out, I get the limit as b approaches infinity of natural log b minus the natural log of the natural log of 2. Okay. So now, if we examine our result, we'll see that this part doesn't really matter because it's a constant. The only part that really matters is the natural log of b. And since b approaches infinity, the natural log of b will also approach infinity, making the result of this integral equal infinity. So that equals infinity. And so, since the value of this integral is infinite, it's not finite, that means that 2 diverges. Okay, So the last series is, as you'll notice, it's a alternating series. So this negative 1 to the power of n means that each element of the series will alternate between positive and negative. So for an alternating series, we can use the alternating series test, which is easy. So there's two conditions for convergence in an alternating series. So the first condition is that the limit as n approaches infinity should equal 0. So if an is the nth term in the series, then that limit should equal 0, and the series, the absolute value of terms in the series should eventually be decreasing. What they mean by like eventually decreasing is it's okay if like a first few finite amount of numbers in the series are increasing. Like if you can have like 1, 2, 3 as part of like the start of your series, but eventually all terms in this series should be smaller than the last. Okay, so in this case, we can see that yes, statement 1 is true, and for 1 over n times natural log of n, each value in the series is going to be smaller than the last because the denominator is going to get bigger with each consecutive term, meaning that each overall term is going to be smaller than the term before it. So therefore, by the alternating series test, 3 is convergent. Okay, so that means that the answer is D. 1 and 3 converge. Okay, question 4 asks, determine whether the following series are absolutely convergent, conditionally convergent, or divergent. And the two series are cosine of k times pi over k to the power of 3/2, and a negative 1 to the power of k over 3 times k. Both are from k equals 1 to infinity. So first, let's just go over what the difference between absolutely convergent, conditionally convergent, and divergent is. So divergent means that the sum of all terms in the series doesn't approach a finite value. So essentially, it approaches infinity or negative infinity. What is the difference between absolutely convergent and conditionally convergent, though? So suppose we have a series A. Suppose we have this series. If this series, the sum of an converges, and the series which is consists of the absolute value of every term in an also converges. So let me write out converges, and this series converges. This is absolutely convergent. So the original series converges, and the series that's obtained by taking the absolute value of each term converges. Then we get absolute convergence. Okay. So the series where the sum of an converges, but the sum of all terms consisting of the absolute value of an diverges, this is conditionally convergent. Okay. And I shouldn't have to write it out, but if both series diverge, that is just divergent. Oh. Okay. When both series diverge, that is divergent. Okay. So we need to determine not only does the alternating series converge, we also have to take the absolute value and determine if that new series converges as well. So let's start by taking a look at series 1. So you'll notice that normally we're given something like we have here in series 2, which is like -1 to the power of k. And this explicitly indicates that we have an alternating series. But in this case, we don't have that. However, we can notice that cosine of k times pi is essentially equal to, that's essentially equal to -1 to the power of k, because cosine times 1 pi is -1, cosine times 2 pi is +1, and then that pattern essentially repeats for all integers. Cosine of 3 pi is -1, and cosine of 4 pi is 1. So that will just repeat, so we can rewrite cosine of k times pi as -1 to the power of k. And the denominator will stay the same. Okay, so let's start off by determining whether this series is conditionally convergent. So since we have an alternating series, we can use the alternating series test. Which states that in order for an alternating series to be convergent, we need two conditions to be true. The limit as n approaches infinity of the absolute value of the term has to approach 0, and the absolute value of the term has to be eventually decreasing. Okay, and so what we'll notice is that 1 over k to the power of 3/2 eventually that limit is equal to 0, meaning that the first statement is true. And since k to the power of 3/2 gets bigger as k increases, that means that 1 over the sequence 1 over k to the power of 3/2 is a decreasing sequence, meaning that since both statements 1 and 2 are true, this sequence is conditionally convergent. Okay, so now to determine whether this is absolutely convergent, we have to determine whether the sequence 1, we need to take the absolute value. So I'm actually going to erase this. Okay, so this is conditionally convergent. Okay. So now after taking the absolute value of each term, we get k equals 1 to infinity of 1 over k to the power of 3/2. So this is convergent by the p-test, which states that a series in the form 1 over n to the power of p is convergent if p is greater than 1. And you'll notice here that the exponent in the denominator is 3/2, which is greater than 1. So this series converges via the p-test, meaning that this series is absolutely convergent. Okay, so this series is absolutely convergent because this series converges and this one does as well. Okay, so we can say series 1 is absolutely convergent. Now moving on to series 2. So series 2, we can start off by determining whether the original series, the alternating series, is convergent. So we'll use the alternating series test again, and we'll notice that this expression, as k approaches infinity, the limit of this term is equal to 0, and that 1 over 3k, since as k gets larger, that sequence will decrease, meaning that statement 2 for the alternating series test is also true. So since both conditions are satisfied, we can say that this series is at least conditionally convergent. Now let's determine whether or not this series is absolutely convergent. So we take the absolute value of all terms, and we end up with this. I can pull the 1/3 out from the summation, since 1/3 is a constant. I can kind of factor it out, and I'm left with this expression over here. And so now, since 1/3 is a constant, we can actually kind of ignore it, and we just have to determine whether this series over here is convergent. And since we have 1 over k, we can use the p-test again. And so remember, the p-test said that for a series in the form 1 over n to the power of p, it is convergent if p is greater than 1. And that series, if p is less than 1, it is divergent if p is less than or equal to 1. So in this case, the exponent for k is 1, meaning that via the p-test, this series is divergent. So since the absolute value of our term, since a series obtained by taking the absolute value is divergent, but the original series was convergent, that means that this series is conditionally convergent. Conditionally convergent. So therefore, our answer would be B. Okay, problem 5 says, consider the series AK, which is equal to 1 over k cubed plus 2k plus 4 times cosine k, from k equals 1 to infinity. Okay, and then they give us 5 statements, which we have to find the one that is correct. Okay, so let's take a look at the first statement. The first statement says, the series is absolutely convergent by the comparison test with 1 over k cubed. So the important word here is absolutely convergent. One of the important words. Okay, so if we have a series AK, it is absolutely convergent if this converges and if the series that consists of the absolute value of each term in the original series also converges. So if both of these series converges, that implies absolute convergence. And the second important fact here is that if this series converges, this series must converge as well. So to show absolute convergence, it suffices to show that the series that consists of the absolute value of each term converges. So it suffices to show that this converges to prove our series AK is convergent. Alright, so first thing we'll do is we'll find, so let me scroll down. We'll find the absolute value of each term in the series. Okay. K equals 1 to infinity. So this is equal to Alright, this is equal to 1 over k cubed plus 2k plus 4. So notice, since our series is from k equals 1 to infinity, this part will always be positive. The part that we have to take the absolute value of is cosine of k. Okay, so yeah, now we have this. The comparison test, the second important part is to determine whether we can use the comparison test to prove that this is convergent. So the comparison test states that, so I'll write it down here. The comparison test states that if we have two series, AN, which is less than BN, then if BN converges, AN converges too, and if AN diverges, BN diverges as well. Okay. In this case, 1 over k cubed is greater than this expression here. And the reason is because our denominator, k cubed plus 2k plus 4, is larger than k cubed. And in the numerator, cosine k is always between 0 and 1. So that means that the numerator is either smaller or equal to 1. So that means that this overall expression is less than this. So in this case, AN is this, and BN is 1 over k cubed. Okay, and I forgot one important caveat. So for a comparison test, AN and BN have to be greater than 0. This is important. So that's why it's really important that we have the absolute value of cosine k here, because otherwise we wouldn't be able to do the comparison test. Okay, so alright, so now I can actually formally use the comparison test. Okay, so by the comparison test, since cosine k over k cubed plus 2k plus 4 is less than 1 over k cubed, and 1 over k cubed converges, and it converges via the p-test. That means that cosine k over k cubed plus 2k plus 4 converges. And therefore, going back to what we initially set out to prove, this series absolutely converges. So A is true. That is our answer. Okay, and I didn't explain it, but the p-test states, so I'll write the p-test down here, that for a series in the form 1 over n to the power of p. It converges if p is greater than 1 and diverges if p is less than or equal to 1. Okay, so going back up to here, p in this case is 3, so that's how we know that 1 over k cubed converges via the p-test. Okay, so A is the correct answer, but just we can also go through the other statements and determine why they are false. So that's what I'll do next. I'll just briefly explain why each statement is false. Okay, so the second statement says the series is divergent by ratio test since the limit of k of the absolute value of ak plus 1 over ak as k approaches infinity is equal to 1. So this statement is false because when we get a result of 1, this does not imply divergent. It implies that the result of the ratio test is inconclusive. So 1, oh, that's a very big eraser. So this result does not imply divergent, it implies inconclusive. Okay, and yeah, the series is convergent. So C says the series is convergent since the limit of ak as k approaches infinity is equal to 0. So this is actually it is the statement that we use for the divergence test, and a result of 0 implies inconclusive as well. It does not imply convergence. Alright, so that's why C is wrong. So B is wrong, C is wrong. Okay, D says a series is convergent by limit comparison test with 1 over k cubed. Okay, so let's go back and look at our series. So as I mentioned, for the normal comparison test, both of the series that we use when comparing have to be greater than 0. And this condition is also true for the limit comparison test. AN and BN have to be greater than 0. However, this is not true for convergence because this is not true in the case of statement D, because cosine k can take on negative values, meaning that not every AN would be positive. So that's why D is false. And then statement E says the series is divergent by divergence test since the limit as k approaches infinity of ak does not exist. Okay, well, we showed when solving for A that the series is convergent, so that statement is just false. Okay, so yeah, our answer is A. Alright, problem set 6 says determine which of the following statements are true and which are false. So statement 1 says the series 1 over k to the power of 4 plus 1 from k equals 1 to infinity is convergent by the limit comparison test with the series 1 over k to the power of 4, which is from k equals 1 to infinity. Statement 2 says the series 1 over k to the power of 4 plus 1 is convergent by the comparison test with 1 over k to the power of 4. And statement 3 says the series 1 over k to the power of 4 plus 1 is convergent by the ratio test. Okay, so basically we have 3 different series tests, and we want to see which ones can be used to show that this series over here is convergent. Yeah, alright. So before we do that though, I just want to highlight this series over here. Since we have 2 comparison tests, both comparison tests rely on comparing one series to another series and using this other series to determine information about the original series of interest. Okay. So basically, I want to determine whether 1 over k to the power of 4 is convergent or not. Okay. And this 1 over k to the power of 4 is convergent by the p-test. So the p-test states that for a series in the form 1 over n to the power of p, it is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Okay, in this case, our p, the exponent is 4, which is why this series is convergent by the p-test. Okay, so now let's move on to the statements themselves. So first up is limit comparison test. Limit comparison test. So the limit comparison test states that for two series A and B, where all terms in the series are greater than 0, if I take the limit as n approaches infinity of the ratio of an over bn, and it equals c, where c is greater than 0 and not equal to infinity, then both an and bn converge or both diverge. Okay. So in this case, to apply the limit comparison test, I would have to take the ratio of both series. So limit as k approaches infinity of, I can do, the order in which I do the ratio doesn't matter, so I'll just put 1 over k to the power of 4 plus 1 on top. Okay, and then I end up with k to the power of 4 over k to the power of 4 plus 1. Okay, and so this limit is equal to 1 anytime we are taking the limit as k approaches infinity of the ratio of two polynomials. So in this case, k to the power of 4 is one polynomial, k to the power of 4 plus 1 is the other polynomial. All that matters is the term with the highest degree. So in this case, k to the power of 4 is the term with the highest degree on top, k to the power of 4 is the highest degree term on the bottom. The ratio of k to the power of 4 over k to the power of 4, that's just 1, which is why our limit is equal to 1. You can also use L'Hopital's rule to show that, but this is faster. Okay. So now, we got our limit, and if according to the limit comparison test, since the result is 1, that means both of these series are either convergent or both are divergent. Well, we know that this series over here is convergent because, again, we said we can see so using the p-test. That means that according to the limit comparison test, this series is convergent as well. So statement 1 is true. Alright, statement 2 is about the comparison test. So the comparison test is similar in that we are comparing two series A and B again, and we have the same condition that an and bn must be greater than 0, and it says that if so suppose we have a series where all an is less than or equal to bn for all n. If bn converges, an converges as well, and if an diverges, bn must diverge as well. Okay, awesome. Alright, in this case, so that means what we have to do here is we have to compare these two terms. Since the denominator here is bigger, that means that this is smaller than 1 over k to the power of 4. So 1 over k to the power of 4 plus 1 is less than 1 over k to the power of 4, which means that our an corresponds to this series, 1 over k to the power of 4 plus 1, and the bn corresponds to 1 over k to the power of 4. And we know that this series, 1 over k to the power of 4, converges, again, via the p-test. And according to the comparison test, if bn converges, an converges as well, which means according to the comparison test, this series over here, 1 over k to the power of 4 plus 1, converges as well. So statement 2 is true. Okay, true. The last statement is the ratio test. Okay, so ratio test says that if we take the limit as n approaches infinity of an plus 1 over an, if the result is less than 1, the series is convergent. If it is greater than 1, it is divergent. And if it is equal to 1, that means that we cannot tell. The results are inconclusive. So it could be divergent, it could be convergent, we don't know. And we would have to use another test. Okay, so in this case, I would take the limit as k approaches infinity of 1 over k plus 1 to the power of 4 plus 1 over 1 over k to the power of 4 plus 1. And that all simplifies to the limit as k approaches infinity of k to the power of 4 plus 1 over, if I expand all of this out, it's going to be k to the power of 4 plus a bunch of other stuff. That's not really important. Like I said before, when we're evaluating the limit of the ratio of two polynomials, all that matters is the term with the highest degree. So on top, the highest degree term is k to the power of 4. On bottom, the highest degree term is k to the power of 4 as well. So the ratio of those two would be 1. So that limit is equal to 1. And according to the ratio test, if the limit is equal to 1, our results are inconclusive, meaning that we cannot conclude for certain whether the series is convergent or divergent. So we cannot conclude that this is convergent, making statement 3 false. So the correct answer would be, since 1 and 2 are true and 3 is false, the correct answer is D. Alright, question 7 says, which of the following statements are always true? So let's start with statement 1. Statement 1 says that if the limit as k approaches infinity of k squared times the absolute value of ak equals 1, then the series negative 1 to the power of k plus 1 times ak converges absolutely. Okay, so given that this statement over here has a limit, we probably want to use one of our series tests to prove that the statement is true or that it is false. So we have our comparison test, limit comparison test, ratio test, and integral test. And of those 4 tests, the integral test and comparison test involve no limits. So this probably relates to either the ratio test or the limit comparison test. The ratio test would not apply here because the ratio test is a ratio between consecutive terms in the series, and we only have ak here. So this probably has to do something with the limit comparison test. Alright, so limit comparison test. Okay, so given that we have two series A and B, and all terms in the series are greater than 0, we would take the ratio as n approaches infinity of an and bn. Okay, and suppose it equals some constant c. It equals c. If c is greater than 0, so if it is positive and it is not equal to infinity, then both an and bn converge, or both diverge. Okay, both diverge. All right. So you might be thinking now, though, that here we have the ratio of two terms. However, in the limit given to us in statement 1, there is, my pen, there's no dividing. We have k squared times the absolute value of ak. Okay, so what we can do is we can rearrange the expression inside the limit. And so I'm going to rearrange it as the limit as k approaches infinity of ak over 1 over k squared. So, and actually, since 1 over k squared is always going to be positive, I can fully extend this absolute value. Okay, and then they tell us that this equals 1. So now I have something that looks very similar to the limit in the limit comparison test. And since it's equal to 1, that means that both ak and 1 over k squared converge. Or both converge or both diverge. However, we know that 1 over k squared converges by the p-test. Okay, the p-test states that if we have a series in the form 1 over n to the power of p, it converges if p is greater than 1, diverges for p is less than or equal to 1. Okay, so in this case our p is 2, so that's why 1 over k squared converges. So therefore we get that ak converges. And so if the series AK converges, series A converges, that means that the alternating series, the corresponding alternating series, which is what we have here, that means that that series must converge. So, yeah. So that means that statement 1 is true. Basically, this, when you say that the regular absolute value of the alternating series converges, that's what AK is. AK is the absolute value of this series. If this converges, that's essentially equivalent to saying that alternating series absolutely converges. Okay, so statement 1 is true. Statement 2 says, if the limit as k approaches infinity of the absolute value of ak equals 0, then the series AK converges absolutely. Okay, so this statement over here looks a lot like the divergence test. So divergence test, and the divergence test states that if the limit as k approaches infinity is not equal to 0, then the series diverges. If the series does equal to 0, that doesn't imply convergence necessarily. It just implies that the test is inconclusive. So this statement over here, this limit, doesn't necessarily imply anything. It doesn't imply anything. So that makes statement 2 false. We can also see that it's false using a counterexample. So in this case, a good counterexample is the series, the harmonic series. So AK is equal to 1 over K. So in that case, if AK is equal to 1 over K, the limit as 1 over K, as K approaches infinity of 1 over K is equal to 0. However, we know that the harmonic series diverges according to the p-test. So that's just a counterexample to see why statement 2 is false. Okay, last statement. Statement 3 says that if this absolute value of AK converges, then AK over K converges as well. Okay, so first thing we can notice is that AK over K is less than the absolute value of AK. Alright, and we know that there is a test comparing two series, which is called the comparison test. And so suppose if we have A and B, and A and Bn, all terms in the series have to be greater than 0. If An is less than or equal to Bn for all n, then if An diverges, Bn diverges too, and if Bn converges, An converges too. Converges too. Okay, so in this case, in our case over here, we are told AK, the bigger series, converges. So if the bigger series Bn converges, then the smaller series must converge as well too. So that means AK over K converges as well, which means statement 3 is true. So that means that 1 and 3 are true, so the correct answer is answer D. Okay, question 8 says, find the radius of convergence R for the power series 2x minus 7 to the power of n divided by 6 to the power of n plus n cubed. Okay, so first what we need to do is we need to find the interval of convergence. The interval of convergence is all values of R for which this series converges. So let me write that down. Interval of convergence. So interval of convergence is all values of R for which the series converges. And this is gonna be a continuous interval. And so the reason this is important is the radius convergence is equal to half the length of the interval of convergence. So interval of convergence. Okay. So yeah. So the way we find the interval of convergence is we take the ratio of two consecutive terms in this series. So an plus 1 and an as n approaches infinity. So in this case, that would equal 2x minus 7 to the power of n plus 1 divided by 6 to the power of n plus 1 plus n plus 1 cubed divided by 2x minus 7 to the power of n divided by 6 to the power of n plus n cubed. Okay, and this all simplifies to 2x minus 7 times 6 to the power of n plus n cubed over 6 to the power of n plus 1 plus n plus 1 cubed. Okay. Alright, So since our limit is only pertaining to n as n approaches infinity, I can pull this 2x minus 7 term out. So I'm going to pull it out. 2x minus 7 times the limit as n approaches infinity of 6 to the power of n plus n cubed over 6 to the power of n plus 1 plus n plus 1 cubed. So usually we're left with like a polynomial, but in this case we have a polynomial plus a constant to the power of a variable n. So it's not as immediately obvious what this limit might be. So in this case, it's helpful to use L'Hopital's rule, which states that if like the numerator, okay, so if the limit of a ratio is, this is in informal terms, so if the numerator and denominator are infinity and infinity, or they're both 0 and 0, the limit of a over b is equal to the limit of a prime over b prime. So basically we can take the derivative of both the numerator and the denominator. So that's what I'm going to do here. So instead of 6n, instead of finding this limit, I'm going to take the derivative of both the top and the bottom. So what I get is, so the derivative of 6 to the power of n would be natural log 6 times 6 to the power of n plus 3n squared divided by natural log 6 times 6 to the power of n plus 1 plus 3n squared plus, okay, wait, this is a lot of 6n plus 3. Yes? Okay, and then okay. I'm going to have to take the derivative, I think, 2 more times, or 3 more times. But essentially, what happens after I take the derivative a few more times is I end up with ln 6, natural log of 6, I think, to the power of 3, it doesn't really matter, times 6 to the power of n divided by natural log 6 to the power of 3 times 6 to the power of n plus 1. And by using L'Hopital's rule and taking the derivative several times, all this polynomial stuff it'll go away. And ultimately, this evaluates to 1/6. Okay. So this is equal to 1/6 over here. I can move all this stuff out of the way. So now that we found the limit, we can go back to calculating the interval of convergence. Okay. So I made a little mistake here. Okay. 2x minus 7 times divided by 6. Okay, so now that we calculated the ratio, so this relates back to the ratio test. So the ratio test states that for a series to converge, this limit over here has to evaluate to less than 1. So this value over here might be less than 1. So according to the ratio test. So I get 2x minus 7. The absolute value of 2x minus 7 is less than 6. So I get 2x minus 7 is less than 6, and 2x minus 7 is greater than negative 6. So if I do I get x is less than 13 halves over here, and then I get x is greater than 1/2 over here, means that our interval of convergence is from 1/2 to 13 halves. So interval of convergence. And that means that the length of that interval is 6, which implies that half of the length, as we said before up here, half of the length is 3. So the answer is A. Okay, question 9 says, find the interval of convergence for the power series 3 to the power of k times x plus 1 to the power of k divided by the square root of k. Okay, so to find the power series, we use the ratio test. So the ratio test says that as n approaches infinity, the ratio of two consecutive terms, if the value of that limit is less than 1, then the series converges. So we essentially use this concept to find the interval of convergence. So what we're going to do is we're going to calculate the limit as k approaches infinity of two consecutive terms of this series. So that would be 3 to the power of k plus 1 over times x plus 1 to the power of k plus 1 over the square root of k plus 1, and that is all divided by 3 to the power of k times x plus 1 to the power of k divided by the square root of k. And this all evaluates to 3 times x plus 1 divided by times the square root of k divided by the square root of k plus 1. Okay, and I can pull out all of this because that doesn't relate to our limit. Our limit is asking what happens as k approaches infinity. So this is equivalent essentially to the absolute value of 3 times x plus 1 times the limit as k approaches infinity of the square root of k over k plus 1. And as k grows infinitely large, the ratio of k and k plus 1 approaches 1. So this evaluates to 3 times x plus 1. So that's our limit. Now to find the interval of convergence, like I mentioned before, we need to set this limit that's less than 1, because according to the ratio test, if the ratio of two consecutive terms approaches a value less than 1, then the series converges. I don't know why I wrote concept up here. It converges. Okay, so now if I solve for this, I get 3x plus 3 is less than 1, 3x plus 3 is greater than negative 1, which gives me x is less than negative 2/3, and x is greater than negative 4/3, which means that A is not the correct answer, C is not the correct answer, and E is not the correct answer. So the answer is either B or D, and they're almost identical, except that for B, negative 2/3 is included in the interval, and in D, it is not included in the interval. So B, it's a closed interval, D is an open interval. Okay, so now how I choose between B and D is I'm going to test what happens when I plug in negative 2/3 for x. So we get 3 to the power of k, and if I plug in negative 2/3, I get 1/3 to the power of k, all divided by the square root of k. And this is equal to 1 over this, this is equal to 1 over the square root of k. Alright, and so now we can use the p-test. So the p-test states that for a series in the form 1 over n to the power of p. It converges if p is greater than 1, diverges if p is less than or equal to 1. So in our case, we have 1 over k to the power of 1/2. 1/2 is less than 1, meaning that this series diverges. So this series diverges by the p-test. So -2/3 is not in the interval. So our interval of convergence is -4/3, -2/3. Okay, so the answer is D. Okay, question 10 asks, which of the following is a power series representation of the function x cubed over 1 plus x squared for absolute value of x is less than 1? Okay, so the power series representation of a function is essentially a way to rewrite a function as the sum of different polynomial terms. So like, yeah, essentially a way to rewrite it as a polynomial. So there's two ways that we can go about this. One way is we can use the Taylor series, which will always work, but that's hard. The other way is to see if we can manipulate a geometric series in some way. Maybe some way this relates to a geometric series. And that's a lot easier to do. So there's a few important concepts to remember. First is the sum of a geometric series. So the sum of a geometric series, so sum of geometric series, this is equal to a over 1 minus r, where a is initial term and r is the common ratio. Okay, and what you'll notice here is the expression given to us in the problem looks a lot like the equation for the sum of a geometric series. So that would mean that the first term, a, equals x cubed, and the common ratio would equal r equals -x squared. So now what I can do is I can rewrite the terms of my geometric series. The general form of a geometric series, if you don't remember, is a times rn. So what I can do now, a is x cubed times -x squared to the power of n, and this is equal to, if I simplify this, I get -1 to the power of n times x to the power of 2n plus 3. Okay, and this is from n equals 0 to infinity. So n equals 0 to infinity. Okay, and now if I look at my answer choices, the answer choice that best matches this is A. So A is our correct answer. Okay, question 11 says, we compute the Taylor series for fx equals 1 over x to the power 4 centered at a equals 10. What is the coefficient of x minus 10 squared in the Taylor series? Okay, so the Taylor series is a way to rewrite any function as a sum of polynomial terms. So you can rewrite it as f of x is equal to the sum of n equals 0 to infinity of Cn, this is a constant, times x minus a to the power of n. So this is a general form of a Taylor polynomial. So the important thing we need to calculate in this case is the coefficient of the x minus 10 squared form term. So the nth constant coefficient, the formula for that is fn, the nth derivative at a, divided by n factorial. So that's the formula for the coefficients. So in this case, we want to find the second coefficient. We want to find the coefficient of the x minus 10 squared term. So it would be c2. And that's equal to the second derivative of f at 10, because the series is centered at 10, divided by 2 factorial. So now I just need to calculate f prime and f double prime. So f prime equals negative 4 to the power of negative 4 times x to the power of negative 5. F double prime equals 20 times x to the power of negative 6. And so if I plug in 10 to the second derivative, I get 20 times 10 to the power of negative 6 divided by 2. And this is equal to 1 over 10 to the power of 5. So the answer is D. Alright, question 12 says, compute the value of this series negative 1 to the power of n times pi to the power of 2n divided by 2n factorial times 3 to the power of 2n. Okay, and as a hint, they say find the power series expansion of cosine of x. So we should definitely find the power series expansion of cosine x. Okay, so the way we find the power series expansion is using Taylor series. So Taylor series is a way to rewrite any function as a sum of different polynomial terms. So this is the general formula, where a, in this case, a is the value at which the power series is centered at. So for this problem, we're going to say that a equals 0, because that just makes things a lot easier. Okay, and then to calculate the coefficient, the formula to calculate the coefficient for each term is the value at a of the nth derivative divided by n factorial. So yeah. Okay, so the important thing to do now is to calculate all the values of the coefficients for cosine of x. So cosine of x. Okay, so first what we'll do though is, notice here we have the nth derivative of f, right? So let's calculate the first few derivatives of cosine x. So I have cosine x is the 0th derivative, I guess, f0. f1 is negative sine x, f2 is negative cosine x, f3 is sine x. And then after that, it just loops back around, and f4 would be cosine x again. Okay, so why is this important? This is going to help us come up with a formula for Cn. So, right. So, and like I said before, the easiest value for a is a equals 0. So I'm going to say at a equals 0, I made this all should be sine of cosine a. So at a equals 0, cosine a equals 1, negative sine a equals 0, negative cosine A equals -1, and then sine A equals 0. So this means that we can find a formula for Cn, and that means that Cn is equal to -1 to the power of 2n divided by 2n factorial. Because the reason I made this a 2n is because we don't really care about what happens on the odd numbers. You know, when we have an odd number here, when n is equal to an odd number in our original formula, we just get 0. Cn evaluates to 0. So all that matters is the coefficients of the even degree polynomials. So basically now I get this should be is equal to -1 to the power of 2n divided by 2n factorial. Okay. So now that I have that, I can plug that back into the expression for f of x. So over here. So what I get now, f of x is equal to n equals 0, -1 to the power of 2n divided by 2n factorial times x, and like we said, a is equal to 0 to the power of 2n. So now I have an expression that is very similar to what they provided in the question. So I have -1 times n divided by 2n factorial. So this means that x is equal to pi over 3. X equals pi over 3, meaning that in order to compute the value of this series, I can plug back pi over 3 into our f of x. And remember, f of x is equal to cosine x, because that's what we've been finding the power expansion of this whole time. So if I plug back in x equals pi over 3 into here, I get the power series that's given to us in the problem, and I can compute the value of the sum of the power series by plugging in pi over 3 into cosine. And so I just have to find cosine pi over 3, which is equal to 1/2. So the sum of the power series is equal to 1/2, meaning our answer is A.